Classical physics, a term encompassing the physics theories developed prior to the 20th century, was for centuries the framework through which humanity understood the natural world. It is often described as the physics of the macroscopic world, the world of everyday experience, where objects are large enough to be observed directly and behave predictably. The foundational principles of classical physics, such as Newton's laws of motion, the laws of thermodynamics, and Maxwell's equations for electromagnetism, were discovered during a time when the world was still largely unexplored, and human knowledge of nature was still in its early stages. But as history would unfold, the same physical laws that explained much of the everyday world were soon found inadequate when it came to explaining the behavior of particles at the microscopic level. Classical physics was grounded in the idea of determinism, that if the current state of a system is known, the future state can be predicted. This idea was born from Isaac Newton's formulation of the laws of motion and universal gravitation in the 17th century. According to Newton, the motion of any object could be precisely predicted if its position and velocity were known. His work laid the groundwork for much of modern science and engineering, establishing physics as a quantitative science. The clarity of these laws seemed to suggest that all the behavior of physical objects could be understood and predicted through mathematical equations. In addition to Newtonian mechanics, another pillar of classical physics was the concept of the continuum of space and time. This was exemplified in the works of James Clerk Maxwell, who in the 19th century unified electricity and magnetism into a single theory of electromagnetism. Maxwell's equations showed that light itself was an electromagnetic wave, and this theory of electromagnetism greatly advanced the understanding of various physical phenomena, such as the behavior of light and the forces between charged particles. Classical physics also included thermodynamics, which governed heat, energy, and the behavior of gases, helping to explain processes like combustion, the operation of engines, and even the function of biological systems. Classical mechanics, in particular, was extraordinarily successful in explaining a vast array of phenomena. The engineering marvels of the 19th century, from the steam engine to the construction of massive bridges and buildings, were all products of classical mechanics. The work of scientists like Newton, Maxwell, and others made it clear that the universe operated according to fixed laws, and those laws could be mathematically described. By the end of the 19th century, the major branches of classical physics seemed to be in a state of completion, ready to explain nearly everything in the physical world. Yet, despite its successes, classical physics encountered significant problems that could not be reconciled within its framework. The most glaring of these issues emerged when scientists began to explore phenomena at the atomic and subatomic levels. One of the most famous problems came from the study of blackbody radiation, the type of radiation emitted by an object that absorbs all incident radiation, making it an ideal emitter of heat. Classical physics predicted that as an object's temperature increased, the intensity of the radiation it emitted should increase without bound at shorter wavelengths, which would result in a so-called ultraviolet catastrophe. However, experimental data did not match this prediction. Instead, the radiation intensity peaked at a certain wavelength and then decreased at shorter wavelengths. Classical mechanics could not explain this phenomenon. The problem of blackbody radiation was not the only issue to arise in classical physics. The study of light also posed challenges that classical theories could not fully explain. For instance, the phenomenon of the photoelectric effect, where light shining on a metal surface causes the emission of electrons, seemed to conflict with the principles of classical wave theory. According to classical physics, light was a continuous electromagnetic wave, and the energy imparted to electrons should depend on the intensity of the light. However, experiments showed that the energy of the emitted electrons was instead related to the frequency of the light, not its intensity, and that light below a certain frequency would not cause any emission, regardless of its intensity. This strange result contradicted classical wave theory and suggested that light behaved differently than previously thought. Another problem arose in the study of atomic structure. In classical mechanics, electrons orbiting the nucleus of an atom were thought to behave like tiny planets orbiting the Sun. According to Maxwell's equations, however, an accelerating charge like an electron moving in an orbit should emit radiation in the form of electromagnetic waves. This radiation would cause the electron to lose energy and spiral inward toward the nucleus, eventually causing it to crash into the nucleus. But this never happened. Atoms were stable, and electrons did not fall into the nucleus, creating a puzzle for physicists. Classical physics had no answer to this conundrum. The search for explanations to these and other problems led to a growing realization that classical physics, while highly successful in many domains, was not enough to describe the behavior of matter at very small scales. The failure of classical physics to explain phenomena like blackbody radiation, the photoelectric effect, and atomic stability indicated that new concepts and theories were needed, concepts that could accommodate the strange behaviors that seemed to defy classical understanding. The shift from classical physics to quantum physics began with the work of Max Planck, who in 1900 proposed a radical new theory to explain blackbody radiation. Planck suggested that energy was not emitted continuously, as classical physics had assumed, but in discrete units or quanta. This insight marked the beginning of quantum theory and represented a sharp break from classical mechanics. Rather than assuming that energy could take any value, Planck proposed that energy was quantized and could only exist in specific amounts. This theory, which was later confirmed by experiments, was a significant departure from classical ideas, which had viewed energy as a continuous flow. Thus, while classical physics had been extraordinarily successful in describing the macroscopic world, its limitations at the microscopic level prompted the birth of a new physics. The idea that energy and matter could behave in unexpected ways at small scales, leading to phenomena that classical physics could not explain, ultimately led to the development of quantum mechanics. This marked the end of the era of classical determinism and the beginning of a new era in physics, one where uncertainty, probability, and wave-particle duality would govern the behavior of matter. In conclusion, classical physics laid the foundation for much of modern science, and its successes were nothing short of revolutionary. However, as scientists began to investigate the fundamental nature of matter and energy at microscopic scales, it became clear that classical physics was not equipped to fully explain the behavior of atoms, light, and subatomic particles. The shortcomings of classical physics would eventually lead to the development of a new framework, quantum mechanics, which would transform our understanding of the universe at its most fundamental level. As we delve further into the limitations of classical physics, it's important to recognize how deeply embedded the classical paradigm was in the scientific worldview. Throughout the 18th and 19th centuries, physics was largely dominated by deterministic laws and the idea that every event in the universe could be explained by a set of mathematical equations. The vast success of classical physics in explaining everything from the orbits of planets to the motion of mechanical devices gave scientists a sense of confidence. Physics seemed like a completed science, with all major mysteries solved. However, nature had other plans. At the core of classical physics was the belief that everything followed predictable, determinable rules. This certainty about the behavior of the physical world began to unravel with the advent of quantum theory. Classical physics simply couldn't explain the peculiarities of atomic and subatomic behavior, leading to the development of entirely new concepts. What we now know as quantum mechanics arose directly from the recognition that classical laws couldn't explain certain physical phenomena. Max Planck's introduction of energy quanta was, of course, just the beginning. His theory revolutionized the way physicists thought about energy. But there were still many challenges ahead. Another major challenge came from the study of the photoelectric effect, which further exposed the limitations of classical wave theory. According to classical physics, light was viewed strictly as a continuous electromagnetic wave. It was assumed that the energy of a wave would increase with its intensity, and a sufficiently bright light should be able to eject electrons from a metal surface, regardless of its frequency. However, experiments showed something entirely different. When light of low frequency was shone on a metal, no electrons were emitted no matter how bright the light was. But when high-frequency light, such as ultraviolet, was shone on the metal, electrons were emitted, even if the light was dim. This was a crucial contradiction of classical theory. Albert Einstein, in 1905, explained this phenomenon by suggesting that light could also be thought of as discrete packets of energy, or quanta. He proposed that these packets of light, now called photons, carried energy proportional to their frequency. Einstein's hypothesis was not just a theoretical explanation, it was confirmed by experimental data and marked a key moment in the development of quantum mechanics. What made Einstein's explanation so significant was the fact that it suggested that energy and light didn't just behave like waves, they also exhibited particle-like properties. This wave-particle duality, which was further developed by physicists like Louis de Broglie and Niels Bohr, would become a cornerstone of quantum theory. This theory radically departed from classical physics by embracing the idea that particles, such as electrons, could exhibit both wave-like and particle-like properties. This was an unsettling idea because it was so counterintuitive to the classical understanding of matter. The conceptual leap required to grasp quantum mechanics is perhaps best understood by considering the underlying assumptions of classical physics. Classical physics posited that objects, whether macroscopic like a baseball or microscopic like an electron, had a definite, predictable position and momentum at all times. This assumption of determinism was deeply embedded in both Newtonian mechanics and electromagnetic theory. However, with the advent of quantum mechanics, scientists began to realize that this deterministic view of the universe was no longer adequate at the atomic and subatomic levels. One of the most famous and startling consequences of this realization came from Werner Heisenberg's uncertainty principle, formulated in 1927. Heisenberg's principle stated that there is a fundamental limit to how, precisely, we can know both the position and the momentum of a particle simultaneously. This was a direct contradiction to classical physics, where it was assumed that, in principle, both could be known with complete accuracy. Heisenberg's uncertainty principle meant that at the quantum level, certainty and predictability were replaced by probability. The universe, at its most fundamental level, no longer operated like a well-oiled clockwork machine at the microscopic level. There were uncertainties that could never be overcome. The uncertainty principle added to the growing realization that classical physics could not fully account for the behavior of matter at microscopic scales. But Heisenberg's principle wasn't just a theoretical curiosity. It had profound implications for how physicists approached the study of atomic and subatomic particles. Rather than trying to determine the exact position and velocity of a particle, quantum mechanics forced scientists to shift their focus to the probability of where a particle might be found or what state it might be in. As quantum mechanics began to take shape, other key figures such as Niels Bohr, Erwin Schrödinger, and Paul Dirac developed new mathematical models and concepts to explain the quantum behavior of particles. Bohr's model of the atom, which incorporated quantum ideas, was one of the first to explain the stability of the atom and the behavior of electrons in discrete orbits. Schrödinger's wave equation, which describes how the quantum state of a physical system changes with time, introduced the concept of wave functions, mathematical expressions that provide the probability distribution of an electron's position. These wave functions were crucial to understanding the probabilistic nature of quantum mechanics. In addition to Bohr and Schrödinger, Paul Dirac made significant contributions by extending quantum theory to include special relativity, leading to the development of quantum field theory, which would later become essential in explaining particle interactions. Dirac's work led to the prediction of antimatter and laid the foundation for quantum electrodynamics, one of the most successful and accurate theories in physics. By the mid-20th century, quantum mechanics had become a fully developed theory that could explain the behavior of subatomic particles. Quantum theory introduced a radically new way of thinking about nature, one that embraced uncertainty, probability, and the strange wave-particle duality of matter and light. It provided explanations for a vast array of phenomena, from the stability of atoms to the behavior of semiconductors and lasers, and it soon became the dominant theory in physics. However, the transition from classical physics to quantum mechanics was not an easy one. The shift in thinking was profound and required physicists to abandon centuries of classical intuition. Where classical physics offered certainty and predictability, quantum mechanics offered only probabilities and uncertainties. The physical world, it seemed, was much stranger and more complex than classical theories had led scientists to believe. Despite the radical departure from classical ideas, Quantum mechanics has since proven to be an extraordinarily successful theory, with its principles being applied in a wide range of technologies and providing a deeper understanding of the universe. Ultimately, the birth of quantum physics marked the end of an era in which classical laws were seen as the ultimate description of nature. As scientists began to explore the strange and fascinating world of the very small, it became clear that a new kind of physics was needed, one that could explain the behavior of particles at the atomic and subatomic level. Quantum mechanics replaced the deterministic worldview of classical physics with a probabilistic, revealing the universe to be far more complex and mysterious than anyone had imagined. In conclusion, classical physics had provided a powerful framework for understanding the macroscopic world, but its limitations at the atomic and subatomic levels became evident in the late 19th and early 20th centuries. The strange phenomena of blackbody radiation, the photoelectric effect, and atomic stability could not be explained by classical theories, and this led to the development of quantum mechanics. Quantum theory challenged long-held assumptions about the nature of reality and forever altered our understanding of the universe. It opened the door to new technologies, new discoveries, and a new way of thinking about the physical world. In the late 19th century, the field of physics was enjoying significant progress, with classical mechanics and electromagnetism providing a powerful framework for understanding many aspects of the physical world. However, there was still an unresolved issue that classical physics could not adequately explain: the behavior of radiation emitted by a black body. A black body is an idealized object that absorbs all incoming radiation, regardless of wavelength, and is a perfect emitter of radiation. Its behavior would turn out to be central in the development of quantum theory. At the heart of the problem was the concept of blackbody radiation, the type of electromagnetic radiation emitted by an ideal blackbody in thermal equilibrium. According to classical physics, specifically Rayleigh-Jean's law, the energy radiated by a black body at a given temperature should increase without limit as the wavelength of radiation shortens. The theoretical predictions suggested that the energy radiated by a black body would diverge at shorter wavelengths, particularly in the ultraviolet range. This result was often referred to as the ultraviolet catastrophe. The classical laws could not explain why the radiation intensity didn't grow infinitely at short wavelengths, as they predicted. The classical theory, based on the principles of electromagnetism and thermodynamics, treated the radiation as a continuous spectrum of frequencies. The assumption was that energy was emitted and absorbed in a continuous manner, with no limitations on the amount or the wavelength of the radiation. This made sense for larger objects such as the warmth of a stove or the glow of a fire. But when applied to blackbody radiation, it led to paradoxical results that contradicted experimental observations. In reality, the intensity of radiation from a black body did not increase indefinitely at short wavelengths, but instead peaked at a certain wavelength and then declined. This discrepancy between the theoretical predictions and experimental observation was one of the major challenges facing scientists in the late 1800s. The problem grew even more urgent as experimentalists sought to measure the radiation emitted by hot bodies. For example, Wilhelm Wien's law, derived in 1893, successfully described the shift of the peak intensity of blackbody radiation to shorter wavelengths as temperature increased. However, this law only worked at high temperatures and did not provide a satisfactory explanation across the entire range of wavelengths. It was clear that something was missing from the classical understanding of radiation. Enter Max Planck, a German theoretical physicist who is often credited with providing the breakthrough that would lay the foundation for quantum theory. In 1900, Max Planck began working on the problem of blackbody radiation, tasked with finding a formula that would accurately describe the experimental data observed by physicists. Planck's approach was different from that of his predecessors. He recognized that the classical assumption of continuous energy might be the source of the problem. Instead of assuming that energy was emitted in a continuous fashion, Planck proposed that energy could only be emitted or absorbed in discrete amounts, or quanta. Planck introduced a formula that explained the observed spectrum of blackbody radiation and matched experimental data. His equation, now known as Planck's radiation law, described how the intensity of radiation emitted by a blackbody varied with temperature and wavelength. The most revolutionary aspect of Planck's law was its introduction of a constant, which came to be known as Planck's constant, denoted by h. This constant was fundamental to his idea that energy levels are quantized. Planck's quantization hypothesis proposed that the energy of electromagnetic waves could only take certain discrete values, proportional to the frequency of the radiation. The energy of each quantum of radiation was given by the formula E equal to h nu, where E is the energy, h is Planck's constant, and nu is the frequency of the radiation. This was an entirely new concept. Energy could not be just any value but must come in discrete chunks. Planck's theory marked a departure from classical physics, which treated energy as a continuous variable. Instead, Planck's approach introduced a fundamental shift, suggesting that at a microscopic level, energy is restricted to specific discrete quantities. His work helped explain why black-body radiation behaved as it did, resolving the ultraviolet catastrophe that had plagued classical physics for years. Planck's radiation law was a triumph of theoretical physics, offering a precise description of experimental data that had been elusive for decades. The implications of Planck's work were far-reaching, though Planck himself did not immediately recognize the full extent of his discovery. He had unknowingly laid the groundwork for the emerging field of quantum mechanics. The concept of quantized energy was a radical departure from the classical view of a deterministic and continuous universe. It was a hint that the microscopic world did not follow the same laws as the macroscopic world. In fact, the idea that energy was quantized led directly to the development of other quantum principles. Albert Einstein, in 1905, would later use Planck's work to explain the photoelectric effect, proposing that light could be thought of as consisting of discrete packets of energy, which he called photons. This explanation of the photoelectric effect would not only support Planck's hypothesis but also confirm that the behavior of light could not be fully explained by classical wave theory. Planck's work also set the stage for other key developments in quantum physics. The quantization of energy had profound implications for the study of atoms and subatomic particles. In classical physics, electrons were thought to move in continuous orbits around the nucleus of an atom. However, classical mechanics failed to explain the stability of atoms or why electrons did not radiate energy continuously, spiral into the nucleus, and collapse. The idea of quantized energy levels would become essential for understanding the behavior of electrons in atoms and led to the development of Bohr's model of the atom in 1913. Additionally, the notion of energy quantization extended far beyond the realm of blackbody radiation. It would form the foundation for the development of wave-particle duality and the theory of quantum mechanics, fundamentally changing our understanding of light and matter. The road to these discoveries was not straightforward, and the transition from classical to quantum physics required a radical shift in the way scientists thought about the nature of the universe. Planck's radiation law not only resolved the issue of blackbody radiation, but also hinted at a deeper truth about the nature of energy and matter. It demonstrated that the physical world operated under rules that were radically different from those that governed everyday objects. For the first time, physicists began to appreciate that the behavior of energy at microscopic scales could not be explained by the principles of classical physics. The universe, it seemed, was governed by probabilistic and quantized laws at small scales, a realization that would have profound implications for the development of future scientific theories. Though Planck initially believed that his theory was merely a mathematical trick to fit experimental data, the success of his approach could not be ignored. It would later become clear that the introduction of quantized energy was not just an isolated incident, but a cornerstone of a completely new way of understanding the universe. The concept of quantization would challenge classical assumptions of determinism and lead to the birth of quantum mechanics, a theory that would soon revolutionize all of physics. As Max Planck's work continued to take shape, his theoretical contributions were pivotal not only in resolving the issue of blackbody radiation, but also in opening the doors to entirely new ways of thinking about energy. Despite Planck's success in resolving the ultraviolet catastrophe, he did not initially recognize the profound implications of his work. However, it soon became clear that his introduction of energy quantization was not just an isolated concept within the realm of blackbody radiation. It was a key step in a broader shift toward a new physical paradigm, one that would lay the foundation for the emergence of quantum mechanics. Planck's quantum hypothesis with its assertion that energy could only exist in discrete amounts, represented a departure from classical physics, which had treated energy as a continuous flow. The concept of discrete energy levels stood in stark contrast to the idea of a smooth, continuous spectrum of energy, a cornerstone of classical physics. This breakthrough implied that, at a fundamental level, the universe might be governed by rules that were fundamentally different from the ones that governed the everyday, macroscopic world. The full ramifications of Planck's work began to unfold with the contributions of other scientists, most notably Albert Einstein. In 1905, Einstein extended Planck's work to explain the photoelectric effect, a phenomenon that had previously defied classical explanation. In the photoelectric effect, light shining on a metal surface caused the emission of electrons, but only if the light had a frequency above a certain threshold. Classical wave theory predicted that the intensity of light, rather than its frequency, should determine whether or not electrons would be emitted. However, experiments showed that only light of sufficiently high frequency could eject electrons regardless of its intensity. Einstein's explanation of the photoelectric effect built upon Planck's idea of energy quantization. He proposed that light, which had been classically treated as a continuous wave, could also be thought of as discrete packets of energy, which he termed quanta or photons. These photons, each carrying a quantum of energy proportional to the frequency of the light, could collide with electrons in a metal and impart enough energy to release them from the metal's surface. Einstein's work was revolutionary because it demonstrated that light exhibited both particle-like and wave-like properties, a concept that would later become a central pillar of quantum mechanics. His work not only confirmed Planck's theory, but also provided experimental evidence for the idea that energy is quantized, further solidifying the shift away from classical ideas. As Einstein's work on the photoelectric effect gained acceptance, it became increasingly clear that the notion of quantized energy was not an isolated phenomenon. It was a concept that extended across various fields of physics and had far-reaching implications for the understanding of atomic and subatomic processes. In the years following Einstein's work, other scientists, such as Niels Bohr, Louis de Broglie, and Werner Heisenberg, expanded on the foundations laid by Planck and Einstein to develop quantum theory in full. One of the most significant developments in this journey came from the study of atomic structure. Classical physics, guided by Newtonian mechanics and Maxwell's equations, struggled to explain the stability of atoms. The classical model of the atom envisioned electrons orbiting the nucleus, much like planets orbit the sun. However, according to classical electromagnetism, an accelerating electron should emit electromagnetic radiation, which would cause it to lose energy and spiral inward toward the nucleus. This should lead to the collapse of the atom, yet atoms appeared to be stable. Classical physics, therefore, could not explain why electrons remained in stable orbits around the nucleus. It was Niels Bohr who, in 1913, proposed a new model of the atom that incorporated the idea of quantized energy levels. Bohr suggested that electrons in an atom could only occupy certain discrete orbits, each corresponding to a specific energy level. These orbits were quantized, and electrons could jump between them by absorbing or emitting energy in discrete amounts, corresponding to the difference in energy between the orbits. Bohr's model was able to explain the stability of atoms and the discrete spectral lines observed in atomic spectra, and it introduced the idea that energy transitions in atoms were governed by quantum principles. Bohr's model marked a pivotal moment in the development of quantum mechanics. It showed that the quantization of energy was not just a theoretical idea, but was essential for understanding the behavior of atoms. Bohr's success, however, was only the beginning. The implications of Planck's energy quanta and Einstein's work on the photoelectric effect began to reverberate throughout the scientific community, leading to further refinements in the emerging field of quantum mechanics. As quantum mechanics began to take shape, the concept of wave-particle duality emerged, another breakthrough that defied classical logic. In the early 20th century, physicists began to recognize that light and matter exhibited both wave-like and particle-like behaviors. Louis de Broglie, in his 1924 dissertation, proposed that particles, such as electrons, could also behave like waves. He suggested that Just as light could exhibit both wave and particle characteristics, particles like electrons could also display both types of behavior, depending on the context of the experiment. This wave-particle duality was confirmed through experiments like the electron diffraction experiment, which demonstrated that electrons, typically thought of as particles, could also exhibit interference patterns, a characteristic of waves. The development of wave-particle duality was a central concept in the development of quantum mechanics, as it helped bridge the gap between the particle-based view of matter and the wave-based view of energy. The dual nature of light and matter became a cornerstone of quantum mechanics, offering a more complete and accurate description of physical phenomena at the atomic and subatomic levels. This duality also highlighted the limitations of classical physics, which had been founded on the assumption that light and matter could be described in either particle-like or wave-like terms, but never both at once. With the rise of quantum theory, the deterministic laws of classical physics were replaced by the probabilistic laws of quantum mechanics. The idea of certainty and predictability in classical physics, where every object's position and velocity could be known precisely, was discarded in favor of the notion that the behavior of particles could only be predicted probabilistically. This shift was encapsulated by Werner Heisenberg's uncertainty principle, which stated that it is impossible to simultaneously know both the position and the momentum of a particle with perfect accuracy. The uncertainty principle was a direct challenge to the determinism that had underpinned classical physics for centuries. As the early 20th century unfolded, the contributions of Planck, Einstein, Bohr, de Broglie, and Heisenberg began to coalesce into a comprehensive framework that fundamentally altered our understanding of the physical world. What began as an attempt to explain blackbody radiation led to the development of quantum mechanics, a theory that would revolutionize not only physics, but also the very way we perceive the universe. Quantum mechanics introduced a radically new way of thinking about energy, matter, and the interactions between them. It showed that, at the microscopic level, nature did not behave according to the familiar, predictable rules of classical mechanics. Instead, it operated according to probabilistic laws, where the outcome of certain events could only be predicted in terms of probabilities. The wave-particle duality, the uncertainty principle, and the idea of quantized energy levels all point to a universe that was far stranger and more complex than anything classical physics had envisioned. In conclusion, the discovery of blackbody radiation was a turning point in the history of physics. The problem of blackbody radiation and the failure of classical physics to explain it prompted the development of new concepts and theories that led directly to the birth of quantum mechanics. Max Planck's introduction of energy quantization and the work of subsequent scientists like Einstein, Bohr, and Heisenberg revolutionized our understanding of the microscopic world. The birth of quantum theory marked the end of an era of classical certainty and the beginning of a new era, in which the universe was governed by principles of uncertainty, probability, and wave-particle duality. This marked the dawn of a new age in physics, one that continues to shape our understanding of the fundamental nature of reality. In the late 19th century, the classical view of physics, which had been extraordinarily successful in explaining the macroscopic world, began to encounter difficulties in the face of new, experimental discoveries at microscopic scales. The study of radiation, particularly blackbody radiation, led scientists to realize that classical mechanics could no longer explain certain phenomena. The failure to account for the energy distribution in blackbody radiation, most notably the ultraviolet catastrophe, was a glaring problem that called for a revolutionary new approach. This was the point at which Max Planck entered the scene with his groundbreaking quantum hypothesis, which would eventually lay the foundation for modern quantum mechanics. Before Planck's intervention, classical physics, as formulated by scientists such as James Clerk Maxwell and Ludwig Boltzmann, predicted that a perfect blackbody, a theoretical object that absorbs all incident radiation and emits radiation at the maximum possible intensity for its temperature, would radiate energy in a continuous spectrum. Classical theory suggested that as the wavelength of radiation became shorter, the intensity of radiation would increase infinitely. This prediction did not match experimental observations, which showed that the intensity of radiation actually peaked at a certain wavelength and then decreased at shorter wavelengths. The classical theory's failure to explain this phenomenon was known as the ultraviolet catastrophe. To solve this problem, Max Planck introduced a radical new idea in 1900, which challenged the long-standing assumption that energy could be treated as a continuous quantity. Planck proposed that energy, instead of being emitted or absorbed continuously, could only be exchanged in discrete amounts, or quanta. His theory suggested that the energy of electromagnetic radiation was quantized and could only take specific values that were proportional to the frequency of the radiation. This was a completely new concept that contradicted classical thinking, where energy was seen as a smooth, continuous flow. Planck's quantum hypothesis was based on the assumption that the oscillators in the walls of a black body responsible for emitting radiation could only take on certain discrete energy levels. These energy levels, according to Planck, were related to the frequency of the radiation by the formula E equal to h nu, where E is the energy of the oscillator, h is Planck's constant, and nu is the frequency of the radiation. This formula, introduced by Planck in 1900, marked the birth of quantum theory. Planck's constant, denoted as h, was a fundamental physical constant that represented the smallest possible unit of energy exchange in nature. It became the cornerstone of quantum mechanics, serving as a bridge between the macroscopic world of classical physics and the microscopic world of quantum physics. Planck's hypothesis suggested that rather than energy being able to take any value, it could only be transferred in discrete units, which became known as quanta of energy. At the time, Planck's quantum hypothesis was a purely mathematical model designed to resolve the problem of blackbody radiation. Planck himself did not fully grasp the full implications of his theory, and he viewed it as a mathematical tool to fit experimental data. However, the profound consequences of Planck's idea would not become apparent until later. Planck's quantum hypothesis fundamentally challenged the classical idea of the continuity of energy. It suggested that nature was not composed of smooth, continuous phenomena at the microscopic level, but rather governed by discrete, quantized elements. This realization would open the door to a new understanding of the physical world. One of the key reasons why Planck's hypothesis was so revolutionary was that it marked the first time that the idea of quantization, which had previously only been considered in terms of very specific phenomena such as the behavior of light in the photoelectric effect, was applied to energy itself. Prior to this, the assumption in classical physics had been that energy could be divided infinitely, with no lower limit on how small the increments of energy could be. Planck's introduction of quantization was a dramatic departure from this view. Although Planck's idea was groundbreaking, it was initially met with skepticism. At the time, the prevailing view in physics was still dominated by classical ideas. The notion that energy could be discrete and quantized seemed highly counterintuitive. However, over time, the implications of Planck's quantum hypothesis would be confirmed by experimental evidence, and it would become a central feature of quantum mechanics. One of the key outcomes of Planck's quantum hypothesis was the resolution of the ultraviolet catastrophe. Planck's formula for blackbody radiation successfully predicted the observed spectrum of radiation, matching experimental data and providing an accurate description of the distribution of radiation at different wavelengths. This was a monumental achievement, as it not only solved a long-standing problem but also introduced a new concept of energy quantization that would be central to the development of modern physics. Although Planck did not immediately recognize the full significance of his work, his quantum hypothesis set the stage for later developments in quantum theory. In particular, the idea of quantized energy would be built upon by other physicists, such as Albert Einstein, who would use Planck's work to explain the photoelectric effect, and Niels Bohr, who would apply the concept of quantized energy levels to explain atomic structure. Planck's work also had implications for the way scientists thought about the nature of light. Prior to Planck's hypothesis, light was understood in classical physics as a continuous electromagnetic wave. However, Planck's idea of quantized energy suggested that light might not only exhibit wave-like properties, but also particle-like properties. This insight was later confirmed by Einstein's work on the photoelectric effect, which demonstrated that light could be thought of as discrete packets of energy called photons. The notion that light exhibited both wave-like and particle-like properties would become a central idea in the development of quantum mechanics, leading to the concept of wave-particle duality. In conclusion, Max Planck's quantum hypothesis was a revolutionary step in the development of physics. It resolved the problem of black-body radiation, which had confounded classical physics, and introduced the radical concept of energy quantization. Planck's theory suggested that energy was not continuous, as classical physics had assumed, but instead existed in discrete units or quanta. While Planck's work was initially seen as a mathematical trick to fit experimental data, it would later prove to be one of the cornerstones of quantum mechanics. His quantum hypothesis opened the door to a new way of thinking about the physical world, and its consequences would reverberate throughout the 20th century, leading to the development of the full quantum theory that would reshape our understanding of the universe. Max Planck's quantum hypothesis was a pivotal moment in the history of physics, one that set the stage for the later developments of quantum mechanics. While Planck himself viewed his hypothesis primarily as a mathematical tool to fit experimental data, it became clear over time that his work had profound implications for the future of physics. The introduction of the concept that energy could only exist in discrete units was not just a fix for blackbody radiation, but a fundamental shift in our understanding of the nature of energy itself. In the years following Planck's work, other physicists built upon his ideas, and the consequences of his quantum hypothesis became clearer. One of the most important applications of Planck's work came in the form of Albert Einstein's explanation of the photoelectric effect in 1905. While the photoelectric effect had been observed in experiments since the 1880s, it had remained unexplained within the framework of classical physics. According to classical wave theory, light should cause the ejection of electrons from a metal surface only if its intensity was high enough, and it should depend on the duration of exposure. However, experimental observations showed that the energy of the ejected electrons depended on the frequency of the light, not its intensity, and that light of a frequency below a certain threshold would fail to cause electron emission regardless of its intensity. Einstein, drawing on Planck's concept of energy quanta, proposed that light was composed of discrete packets of energy or photons, each carrying energy proportional to its frequency. This was a groundbreaking shift in thinking, as it suggested that light was not just a continuous electromagnetic wave, as classical theory had proposed, but also had particle-like properties. Einstein's explanation of the photoelectric effect confirmed Planck's idea of quantized energy and extended it to explain a broader phenomenon. Einstein's work earned him the Nobel Prize in Physics in 1921, and it marked a significant confirmation of the quantum hypothesis, helping to further cement the validity of Planck's ideas. Planck's quantum hypothesis also played a critical role in the development of Niels Bohr's model of the atom. Bohr, building upon Planck's work, proposed that electrons in atoms could only occupy certain discrete energy levels. These energy levels were quantized, meaning that electrons could only absorb or emit radiation in discrete quantities corresponding to the difference between these levels. The quantization of energy levels was a radical departure from classical physics, which had treated electron orbits as continuous. Bohr's model of the atom successfully explained the discrete spectral lines observed in hydrogen atoms, and it provided a framework for understanding atomic structure. This model, while later modified, was one of the early triumphs of quantum theory. The notion of quantized energy levels also paved the way for the development of quantum mechanics. In 1925, Werner Heisenberg formulated the matrix mechanics representation of quantum mechanics, and shortly thereafter, Erwin Schrödinger developed his wave mechanics formulation. Both of these new theories were based on the idea of quantization of energy, a direct consequence of Planck's work. Schrödinger's wave equation, which described the behavior of quantum systems, relied on the concept of energy quantization to predict the allowed energy states of particles such as electrons. The development of quantum mechanics was thus deeply rooted in the principles laid out by Planck's quantum hypothesis. One of the key features of quantum mechanics is the concept of wave-particle duality, the idea that light and matter exhibit both wave-like and particle-like properties. While Einstein's work on the photoelectric effect helped establish the particle-like nature of light, the wave-like behavior of light had already been well established by classical physics through experiments like Thomas Young's double-slit experiment. However, with the advent of quantum theory, it became clear that particles, such as electrons, could also exhibit wave-like behavior. This realization came from Louis de Broglie's 1924 theory, which proposed that all matter, not just light, could exhibit wave-like properties. This was a direct consequence of Planck's quantum hypothesis, as it showed that energy, whether in the form of light or matter, was governed by quantization and exhibited both particle and wave characteristics. The concept of wave-particle duality challenged the classical view of the world, which had treated light and matter as separate entities. Light was a wave, and matter was made of particles. The quantum revolution, ignited by Planck's work, introduced the idea that these two seemingly distinct categories were not so easily separated. The wave-particle duality concept was experimentally confirmed through electron diffraction experiments in which electrons, typically thought of as particles, displayed interference patterns characteristic of waves. As quantum theory developed, it became increasingly clear that the classical world of certainty and determinism, in which every object's behavior could be precisely predicted, was being replaced by a new understanding of uncertainty and probability. This shift was epitomized by the Heisenberg uncertainty principle, formulated in 1927, which stated that it is impossible to simultaneously know both the position and momentum of a particle with absolute precision. The uncertainty principle, along with the probabilistic nature of quantum mechanics, fundamentally challenged the deterministic worldview of classical physics. It suggested that the universe at the quantum level was governed by chance and probability, rather than by fixed laws that could predict the future with certainty. The probabilistic nature of quantum mechanics was another consequence of Planck's quantum hypothesis. Planck's idea of quantized energy levels had introduced the notion that energy could only be exchanged in discrete amounts. But as the quantum theory evolved, it became clear that the behavior of particles, such as electrons, could only be predicted in terms of probabilities. The exact location or momentum of a particle at a given moment could not be determined with certainty. Instead, quantum mechanics could only give the probability of finding a particle in a particular state. This probabilistic nature of quantum mechanics, which was formalized in the work of Schrödinger and Heisenberg, was a major departure from classical physics. In classical mechanics, the behavior of particles and objects could be predicted with high accuracy, given sufficient information about their initial conditions. But in the quantum world, even with complete knowledge of a system, the future could only be described probabilistically. The implications of Planck's quantum hypothesis extended far beyond the realm of theoretical physics. Quantum mechanics has had a profound impact on technology, giving rise to innovations such as semiconductors, lasers, and magnetic resonance imaging, MRI. The development of quantum theory has transformed fields such as computing, communications, and medicine, and it continues to be a driving force in scientific and technological innovation. The ongoing pursuit of quantum computing, for example, promises to revolutionize computing power and open up new possibilities for processing information at unprecedented speeds. In conclusion, Max Planck's quantum hypothesis was the cornerstone of a new era in physics, one that would replace the deterministic worldview of classical mechanics with a probabilistic and quantized understanding of the universe. Planck's revolutionary idea that energy could only be exchanged in discrete quanta resolved the long-standing problem of blackbody radiation and set the stage for the development of quantum mechanics. His work, followed by the contributions of Einstein, Bohr, Heisenberg, and others, reshaped our understanding of matter, energy, and the fundamental laws of nature. Quantum mechanics, born from Planck's quantum hypothesis, continues to be one of the most successful and far-reaching theories in the history of science. The introduction of the Heisenberg uncertainty principle marked a monumental shift in the way scientists understood the behavior of particles at the quantum level. Prior to this, classical physics was built on the idea of determinism, the belief that if the current state of a system was known, the future could be predicted with absolute certainty. However, this certainty was upended by Werner Heisenberg's work in the 1920s, which introduced the concept that, at the quantum level, certain pairs of properties of particles, such as position and momentum, cannot be precisely measured or known simultaneously. The more accurately one property is measured, the less accurately the other can be known. This principle fundamentally altered the way physicists approached the study of particles and their interactions. Heisenberg's uncertainty principle emerged from his analysis of the limitations inherent in quantum mechanics. While classical physics relied on the assumption that it was possible to measure the position and velocity of an object with infinite precision, quantum mechanics revealed that at extremely small scales these properties could never be known simultaneously with perfect accuracy. The uncertainty is not due to measurement limitations, but is inherent to the nature of quantum objects. Heisenberg demonstrated that the uncertainty in the measurement of position, deltax, and momentum, deltap, is inversely related, such that the product of these uncertainties is always greater than or equal to a constant, h4πa, known as Planck's constant. This mathematical expression is a direct manifestation of the fundamental limitations that quantum systems impose on measurement. The implications of the uncertainty principle were profound. It suggested that the very act of measuring one property of a particle disturbs it in such a way that the measurement of the complementary property becomes less precise. This was a radical departure from classical thinking, where objects could be measured without significantly influencing their state. In the quantum world, however, observation itself alters the system. This concept was illustrated with the famous example of a photon interacting with an electron when we attempt to measure the position of an electron by shining light on it. The light interacts with the electron, disturbing its momentum. The more precisely we try to measure the electron's position, the more the uncertainty in its momentum increases. The uncertainty principle also had philosophical implications. It challenged the very notion of objective reality as understood in classical physics. In classical mechanics, the universe was assumed to operate like a well-oiled machine, governed by predictable laws. However, quantum mechanics, with the uncertainty principle at its core, revealed a universe governed by probabilities rather than certainties. The exact state of a quantum system could not be fully known, only the likelihood of finding it in a particular state. This new probabilistic framework was central to the development of quantum mechanics and led to the adoption of a new mathematical structure, the wave function, which describes the probabilities of various outcomes in a quantum system. The Heisenberg uncertainty principle also had a significant impact on how scientists understood atomic and subatomic processes. For example, the behavior of electrons and atoms could no longer be described in deterministic terms. Classical models, such as the Bohr model of the atom, were based on the idea that electrons orbited the nucleus in fixed paths. However, the uncertainty principle showed that electrons did not have precise orbits or trajectories. Instead, their position and momentum could only be described probabilistically. This insight laid the groundwork for the development of quantum mechanics as a full theory of atomic structure, and led to the creation of more advanced models, such as Schrödinger's wave mechanics and the concept of electron clouds around atomic nuclei. In conclusion, the Heisenberg uncertainty principle was a groundbreaking idea that reshaped our understanding of the microscopic world. It shattered the classical view of a deterministic universe and introduced a new paradigm based on uncertainty and probability. Far from being a limitation of the theory, the principle is a fundamental feature of quantum systems, one that has been confirmed through countless experiments, and is crucial for understanding the behavior of particles at the quantum level. Its far-reaching consequences continue to influence fields ranging from particle physics to quantum computing, demonstrating the profound and lasting impact of Heisenberg's insight. The concept of wave-particle duality stands as one of the most intriguing and paradoxical elements of quantum mechanics, reshaping our understanding of light and matter. Before the 20th century, light was traditionally thought of as a wave, a view established through the work of Thomas Young's double-slit experiment in 1801. This experiment demonstrated that light exhibited interference patterns, a property typically associated with waves, not particles. On the other hand, matter such as electrons was believed to be composed of discrete particles, a view that had been solidified by Newton's corpuscular theory of light. However, the advent of quantum mechanics in the early 1900s challenged these classical distinctions, leading to the realization that both light and matter could exhibit properties of both waves and particles, depending on the experimental conditions. The first significant breakthrough in understanding wave-particle duality came from Albert Einstein's explanation of the photoelectric effect in 1905. Einstein proposed that light, which had been thought of solely as a wave, also had particle-like properties. In the photoelectric effect, when light shines on a metal surface, it can eject electrons from the metal. Classical wave theory predicted that the energy of the ejected electrons would depend on the intensity of the light. However, experiments showed that the energy of the electrons depended on the frequency of the light, not its intensity. Einstein explained this by suggesting that light consisted of discrete packets of energy, or quanta, later known as photons. This work earned Einstein the Nobel Prize and confirmed that light had particle-like characteristics. Wave-particle duality didn't end with light. In 1924, Louis de Broglie proposed that particles, such as electrons, should also exhibit wave-like properties. He suggested that any particle with momentum could be associated with a wave, and the wavelength of this wave would be inversely proportional to the particle's momentum. De Broglie's hypothesis was confirmed in 1927 by the Davison-German experiment, which showed that electrons could diffract, much like waves of light. This experiment solidified the idea that not only light, but also matter could display both wave and particle characteristics, leading to the dual nature of particles at the quantum level. The implications of wave-particle duality were profound and far-reaching. It undermined the classical view of the universe, which had firmly separated the domains of waves and particles. In the quantum world, these boundaries blurred, with both light and matter displaying behaviors that seemed contradictory in the classical sense. For instance, in the famous double-slit experiment, electrons, when not observed, behave like waves and interfere with themselves, creating an interference pattern. However, when observed, electrons act like particles, creating a pattern typical of individual particles passing through one slit or the other. This paradoxical behavior is a direct manifestation of wave-particle duality. Wave-particle duality also led to the development of quantum mechanics as a probabilistic theory. In classical mechanics, objects followed deterministic paths with their future states predictable from initial conditions. However, quantum mechanics, with its wave-particle duality, introduced uncertainty and probability. The wave-like behavior of particles meant that their positions could no longer be determined with certainty but only as probabilities. The famous Schrödinger equation, a cornerstone of quantum mechanics, describes the behavior of particles as wave functions, which give the probability of finding a particle in a particular state. The significance of wave-particle duality is not confined to theoretical physics. It has had practical applications in technology and modern science. For instance, the development of technologies like electron microscopes relies on the wave-like properties of electrons. Similarly, the understanding of wave-particle duality has been instrumental in the development of quantum computing, where quantum bits, qubits, exploit the superposition of wave-like states to perform computation far more efficiently than classical computers in certain scenarios. In conclusion, wave-particle duality is a fundamental concept of quantum mechanics that revolutionized our understanding of nature. It bridged the gap between the classical concepts of particles and waves, revealing that at the quantum level, entities like light and matter do not fit neatly into either category. This duality is at the heart of quantum theory, leading to the development of a new probabilistic framework for understanding the behavior of particles. It has shaped everything from our understanding of atomic structure to the development of groundbreaking technologies, demonstrating its deep and lasting impact on both science and technology. The development of quantum mechanics was a groundbreaking shift in our understanding of the microscopic world, challenging the classical view of a deterministic universe. One of the key concepts that arose from this shift was the notion of wave-particle duality, which proposed that particles, such as light and electrons, exhibit both wave-like and particle-like properties. This paradoxical behavior was highlighted by the work of Niels Bohr, whose model of the atom incorporated quantized energy levels for electrons, marking the beginning of a new understanding of atomic structure. Bohr's model showed that electrons could occupy only certain discrete orbits around the nucleus, and these orbits corresponded to specific energy levels. This quantization was a direct result of Planck's work on blackbody radiation, which introduced the idea that energy is emitted or absorbed in discrete units rather than continuously. The implications of Bohr's model were profound, as it explained the stability of atoms and the discrete lines observed in atomic spectra. However, Bohr's model was limited in its ability to explain the behavior of more complex atoms, and it soon became clear that a more general theory was needed to fully describe atomic and subatomic phenomena. This led to the development of quantum mechanics, a theory that provided a more comprehensive framework for understanding the behavior of particles at the quantum level. One of the most significant features of quantum mechanics is the concept of the wave function, introduced by Erwin Schrödinger. The wave function describes the probability distribution of a particle's position, momentum, and other properties, and it forms the basis of quantum mechanics. The wave function represents the quantum state of a system, and its evolution is governed by Schrödinger's equation. This equation allows physicists to calculate the probability of finding a particle in a particular state, providing a statistical description of the system rather than a deterministic one. This shift from determinism to probability was one of the most radical changes brought about by quantum mechanics. The uncertainty inherent in quantum mechanics, as formalized by Heisenberg's uncertainty principle, further highlighted the departure from classical physics. According to this principle, it is impossible to simultaneously know both the position and momentum of a particle with absolute precision. This uncertainty is not a result of measurement limitations, but is an intrinsic feature of the quantum world. Quantum mechanics also introduced the concept of superposition, which states that a quantum system can exist in multiple states at once. This phenomenon is best illustrated by the famous thought experiment known as Schrödinger's cat, which depicts a cat that is both alive and dead until observed. This idea of superposition has been experimentally confirmed in systems such as electrons and photons, which can exist in multiple states simultaneously, and it is one of the key features that differentiate quantum mechanics from classical physics. Superposition has important implications for quantum computing, where qubits can exist in multiple states simultaneously, enabling quantum computers to perform certain types of calculations exponentially faster than classical computers. Another key aspect of quantum mechanics is entanglement, a phenomenon where particles become correlated in such a way that the state of one particle instantaneously affects the state of another, no matter how far apart they are. This non-local correlation, which Albert Einstein famously referred to as spooky action at a distance, was experimentally confirmed in the 1960s by physicists like John Bell. The realization that particles can be entangled and exhibit non-local correlations has led to the development of quantum information theory and quantum cryptography, fields that have potential applications in secure communication and quantum computing. In conclusion, the development of quantum mechanics marked a revolutionary departure from classical physics. The introduction of concepts such as wave-particle duality, wave functions, uncertainty, superposition, and entanglement provided a new framework for understanding the behavior of particles at the atomic and subatomic levels. These ideas not only reshaped our understanding of the physical world but also paved the way for groundbreaking technologies like quantum computers, quantum cryptography, and advanced materials science. The legacy of quantum mechanics continues to shape the future of scientific research and technological innovation. The development of quantum mechanics fundamentally altered our understanding of the universe. Prior to its emergence, classical physics, based on the works of Newton and Maxwell, dominated the scientific landscape. Classical physics, with its deterministic laws, offered clear predictions and a seemingly predictable universe. However, at the atomic and subatomic scales, classical physics began to fail, prompting the birth of quantum theory, which is based on principles that defy classical intuition. Central to this revolution was the realization that at the microscopic level, particles and waves are not distinct, but are intimately connected in a way that classical physics could not explain. One of the key pillars of quantum mechanics is the concept of quantization, first introduced by Max Planck in 1900. Planck's work on blackbody radiation led him to propose that energy is not emitted or absorbed in a continuous manner, but in discrete amounts, or quanta. This insight directly contradicted the classical idea that energy could vary continuously and was crucial in leading to the development of quantum theory. This discrete nature of energy became foundational to the field, showing that the physical world behaves very differently at small scales than it does in our everyday experience. The wave-particle duality of light and matter is another cornerstone of quantum mechanics. Historically, light was seen as a wave, supported by experiments like Thomas Young's double-slit experiment, which demonstrated the wave nature of light through interference patterns. However, Experiments such as the photoelectric effect, explained by Albert Einstein in 1905, showed that light also behaves like a particle. Einstein proposed that light could be thought of as discrete packets of energy, or photons, each with energy proportional to the frequency of the light. This particle-like behavior of light was confirmed by further experiments, and it prompted scientists to reconsider the nature of not just light, but all forms of matter, including electrons. Niels Bohr's model of the atom further expanded quantum theory by introducing the idea that electrons in atoms occupy discrete energy levels or orbits, rather than being able to occupy any arbitrary orbit. Bohr's model successfully explained the hydrogen spectrum and introduced the concept of quantized energy states in atoms. This quantization, although later refined, was crucial in understanding atomic structure and provided evidence for the emerging quantum theory. The Heisenberg uncertainty principle, formulated by Werner Heisenberg in 1927, introduced another groundbreaking concept that distinguished quantum mechanics from classical physics. The principle states that it is impossible to simultaneously know both the exact position and the exact momentum of a particle. This was not due to limitations in measurement, but rather an inherent property of quantum systems. The uncertainty principle challenged the classical belief in determinism, suggesting that, at the quantum level, the act of measurement itself introduces inherent unpredictability. Another important principle of quantum mechanics is superposition. This states that a quantum system can exist in multiple states at once, only collapsing into a definite state when measured. The famous Schrödinger's cat thought experiment illustrated this paradox, where a cat in a sealed box can be both alive and dead until observed. Superposition is not just a theoretical concept. It has been experimentally verified in systems such as photons and electrons. Superposition underpins the concept of quantum computing, where quantum bits, qubits, can exist in multiple states simultaneously, allowing for vastly greater computational power compared to classical computers. Entanglement is a further revolutionary concept introduced by quantum mechanics. In entanglement, two particles can become correlated in such a way that the state of one particle instantaneously affects the state of the other, no matter how far apart they are. This non-locality of quantum mechanics was famously described by Einstein as spooky action at a distance. Yet, it has been experimentally confirmed through Bell's theorem and various subsequent experiments. Quantum entanglement has profound implications for information theory, particularly in the fields of quantum computing and quantum cryptography, where it offers possibilities for secure communication. In conclusion, the development of quantum mechanics was a monumental shift in scientific understanding. The principles of quantization, wave-particle duality, uncertainty, superposition, and entanglement have transformed our understanding of the physical world. These ideas not only challenge our intuitive understanding of reality, but have also paved the way for groundbreaking technological advancements, such as quantum computing and quantum cryptography. As we continue to explore the quantum realm, these principles will likely continue to reveal new and surprising insights into the nature of the universe.